Hello there, Math 125 fans. I've been meaning to make this video for a long time. I'm going to talk about work. This is part of my exam 2 review. I think about work as two separate types of problems. Again, we're just doing the magnitude of work. So if you really want to study work, you need to take a physics course and study vectors. But we're just studying something lifted straight up. Okay, so we have this definition that says it's force times distance. So if you lift a 3-pound book 2 feet, we call it 6 foot-pounds. For some students, that's really bizarre. They've never heard such units. But it is valuable to have some way to measure the effort, and compare different things. If a machine, an excavator, is picking up dirt all day, how many foot-pounds of work can it do before it runs out of gas? So it's a useful measurement of things. We're just going to use it as a laboratory to practice setting up calculus. Calculus is really good, especially integrals are good, for approximating things that come from the definition of products. Now, this is a problem you have to set up and label, and there's units, so there are confusions people have, and I have a lot of resources to help with that. But I thought I would add one more resource, which is some visuals. So I just want to explain the concept of leaky buckets and stack of books. This is something I invented years ago, and I think for me it helps me think through the problems because I think there are two distinct types of problems, and then I'll separately do a few exam questions. Okay, so here we go. This is a video of me doing a leaky bucket. I think of a leaky bucket as something that's getting lighter or heavier as you lift it, and it's just one object. So my object is going to be this red Solo cup. I've poked a hole in the bottom, and let's see what I did here. You can't hear me speak there. I turned that off. So I filled it with water. Okay, there's a hole in the bottom. So in a moment, I'm going to lift it up. It's kind of hard to see the water, but it's going to get lighter as I lift. So I can't just say, 2 pounds times 3 feet, because it's not 2 pounds the whole time. It's changing. So let's watch it go. Leaky bucket. I slowed it down a little bit. So water's leaking. It's hard to see here. I needed to use a better backdrop. You can see it here when I get up here. So let's just pretend I lifted about 4 feet. I estimated, I'll estimate the work, but it got lighter as I went. Okay. Unfortunately, my belly didn't get any smaller. Okay, so that's what I would call a leaky bucket problem. And I'll talk about those in just a second, but it's a problem where you're trying to do force times distance, but the force is changing as you lift. Okay? And those I can maybe let's just talk about that for a second. I estimated, I looked up approximately what the water weighed at the bottom, what it weighed at the top. It was going 4 feet. For this one, I'll do it in imperial units, which means I don't have to worry about gravity because there's all these little things. I'll talk about this other example in a second. So right now we're over here. Okay, so in this setup, what's changing is the force. And how we think about it is we break it up into pieces. So we say from here to here, how much work was done. And then from here to here, how much work was done. And then from there to there, how much work was done. And so in those situations, what we're calling delta X is that little bit of distance that you're lifting as you go. Okay, so it's very different from this other example I'm going to do in a second. Okay, so that's what I'm calling delta X. Let's pretend it's the same. I do several measurements. What I now need is the force. So how much does it weigh? In this case, I'm going to assume that it leaked out at a positive rate, and now it's pattern finding. And you can actually label it however you want. So let's say you wanted to label the bottom 0, which is not the right or wrong way to do it, and you wanted to label the top 4. This confuses students that they get to pick. No one in math likes to pick. But if I tell you that the force is going out at a constant rate, in other words, it's linear, then you can find the equation of the line from those two data points. This is not really a work thing. It's just I can get it if it's at a constant rate. So what do I know? I know that the slope is 0.5 minus 0.2 over 0 minus 4. So it's point, I didn't calculate this ahead of time. I just wanted to talk about it. Okay, so the force is negative 0.3 over 4. Look at how lazy I'm being. That's it. So what you would say is, at this x value, I would like to plug in the x, multiply times delta x. And then at the next x value, I'd like to get the x, multiply by x. And then at the next x value, I'd like to do the same. I'd like to add those up. So there's really digging deep into what's going on. But the short answer is you just need to integrate. So what we're trying to do is add up the force times the x value times the width. The more and more subdivisions we do, the more accurate we're going to be. And so we want to do the integral from 0 to 4 of all of this. So in a leaky bucket problem, I often tell students, if you're thinking about this is the distance. It's the little incremental distance. Newton might have said infinitesimal. At least that's what I've read. I don't know Newton. And this would be to represent the force. So there's one example, and that's the way the book kind of presents it for all situations. But I really just use that in a situation where I can tell it's something getting lighter or heavier as I lift. All right, let's see another one. So then this other situation, this is just conceptual, but I feel like this is key. So here's another situation, a stack of books. And that's my own invention. I'm pretty sure I'm original with this one. I haven't heard other people say it. So here I have placed a stack of books, and I've lifted them up. You can still see them behind my head back there. Okay, so I'm going to lift the first book to the top of this bookcase, and then the next book, and the next book, and the next book. Let's watch. So to me, this is a fundamentally different type of problem. I'm still trying to measure the work I'm doing, but that was less work than the next book. You might think about what's different. And then I lifted the next one. Ooh, I'm tired. And then I lifted the next one. And the next one, I got a lot faster there. I sped it up a little bit. Then here I slowed it down. Whoa, look at me go. As I'm lifting it, it's not getting heavier or lighter. The force is not changing. What's changing is how far I'm lifting. The bottom one had to be lifted further. That's a very different problem. Okay, so what's different here, and I looked online for the weight of a typical book. And it's about, and this one I'm going to do in metric. I tell students the moment you see kilograms is when you multiply by 9.8. And the problem is that this is a mass, whereas pounds is not a mass. Unfortunately, it's a little thing. Most of these problems we're going to do in meters. And so if I converted, it's hard to measure a book's weight in meters or a book in meters. But let's see, 100 centimeters is a meter. So I'll multiply times 100. So I guess 20. Oh, maybe that's nice. 20 kilograms per meter. And hopefully I did all that right, but that part doesn't really matter. Okay, that's not changing. We're going to call that the density of a book. I just want to give something that was similar to what we see in practice. Let me move this over so we can just focus on this. So what do we do here? Same thing we label. We label however we want. We can label the top 0. We can label the bottom 0. We don't have to use X. We could use Y. In fact, sometimes in these problems, I use Y equals 0 because of the nature of the problems that come up when we do pumping. So let's just, for fun, do this. And it's about 1.2 meters up, I just estimated. So I am saying I'm lifting 1.2 from the bottom. So the last book gets lifted 1.2 meters, but the first book doesn't. It gets lifted quite a bit less. Okay, so that's the job we need to figure out. So then what I say is, if I call a given book at Y, and I label it with a thickness delta y, there's two questions to ask. So what I think about is just one book. Let's pick one book here, right here, and think about how much effort it takes to lift that one book. What's going to be lifted to the top? Let's pretend that it started, I don't know, 0.3 meters from there. How far does it get lifted? So that particular book is going to get lifted 1 minus 0.3, or in other words, 1.2. Sorry, I said 1.2. 1.2 is the distance to the top. All I'm doing, and I don't know how to make this more clear, this is 1.2 meters. The book that I'm picking up is 0.3 meters. Students will say, when do I subtract and when do I add? Just look at what this is. Okay, so 1.2 minus that, so it's 0.9. So that book is going to be lifted 0.9. How much does it weigh? Well, we would need its thickness. So let's let delta x be the thickness of the book of one book. And when we do this in practice, we assume they all have the same thickness. If I'm doing this in this practical example, I'd have to estimate the thickness for each one. So I'm going to take that thickness, which would be in meters, and I'm going to multiply it times 20. Think about what that represents. So if you have that's going to tell you how much that book weighs. Except that I forgot something. That will tell you the mass of one book. The part I forgot is we have to multiply by 9.8. Oh, I almost made the mistake. So you only multiply by 9.8 when it's in kilograms. That converts it to newtons. That's the added little thing in metric you have to think about. All right. So once you multiply by 9.8, it becomes the force. So it's interesting to see that. That's just the weight of one book. And now we got to figure out the distance it's lifted. Well, the distance that book was lifted was 0.9, but what's the pattern? What if you change the y? And I should be using delta y, darn it. So this is 1.2 minus y, and that's the distance. Now, if you had labeled the top 0, it would have been based off of that, and actually would just be y. Okay, so what do we have? Now we have the integral. Now, in this case, I didn't have books all the way up, so maybe the first book was at y equals, let's say, 0.6 meters, and the book at the bottom was y equals 0, so it would be 0 to 0.6 in my labeling. Okay, and then I would do force times distance, but I'm going to put the distance first because I want to put that dy at the end. So there's the distance. This is 20 dy. There's the force. So as you break this down, and you can also think about what the units are. This is distance in meters. This is force in newtons. And this gives you Newton meters. Okay, so that was a lot. I know, every time I do this, I fail in some way. But I'm desperately trying to find a way to clear this up for students. So what do we do? You identify, is it one object that's getting lighter or heavier as you lift it? It's a leaky bucket. In a leaky bucket problem, you're just trying to figure out the force at a given spot along the way. And then you're integrating and multiplying times dx. In a stack of books problem, and that would be a problem in a moment. We'll talk about like pumping water out of a container is an example of a stack of books problem. You pretend that the water is a stack of books. And you ask yourself, how much work to lift that book? So in these problems, you label one slice at the beginning and say, where does it go? Where does it end up? Okay, I'll do some examples of that, but I hope that gives a better picture of how we think about these problems. It's pattern finding. Pattern finding is always one of the hardest skills for math students. But I hope that helps give you an idea of what we're trying to do. All right.